Thank you so much. So then let's get started. So it's my great pleasure to introduce Hussain Mawahi. So Hussein is a research scientist at Google Research, and he's working on optimization, and currently he's working on theory of deep learning. So he graduated from UIUC, and then he did a postdoc at MIT, and he recently organized a couple of very interesting workshops. For example, uh, modern trends in non-convex optimization for machine learning in ICML 2018, uh, understanding and improving generalization in deep learning in ICML 2019, and the competition, namely predicting generalization in deep learning in Europe's 2020. So I also add that, so Hossein, probably without him knowing this, he influenced my career a lot. So I know him since I did an internship at Google, and he asked me the following question. So he asked me, Bahram, you are working to finding these representative subsets for all sorts of different applications. Can you find a subset for training machine learning model? In particular, when we don't know the exact form of this model. And I could never get rid of these questions. I started working on this when I was at Stanford, and I'm still working on it. And I should thank him probably for this.
Oh,
Thank you so much. And with this, saying the stage is yours. And thanks for joining us today.
okay. Thank you very much, Baharan, for the nice introduction. I'm flattered, especially about the last comment, and I'm very happy to be here. So today I'll talk about self-distillation, which is a method that is getting very popular recently in the deep learning community. But as usual, there are a lot of mysteries around it, and hopefully today we can demystify some of those. This is joint work with my collaborators, Mehdad Parashtavar and Peter Bartlett. And this work is available on arXiv. So if you want more details, you should feel free to visit the paper, because this is because of the talk, I have to compress a lot of the details and skip some of those. But you can find most of the details in the paper. Also, this is a accepted paper, so you can find it on NERP's website, NERP's this year 2020. But the archive version, I prefer that because it doesn't have page limit, so I could write it more clean and without this dilemma of compressing your your paper and then losing some information. Okay, so let's get started. So what is self distillation? So suppose you have a training set. The inputs are shown here by x0 and the labels are shown by y0. And then you feed those into your architecture or whatever learning architecture that you have. And after training is done, it produces a model, right? Which I show here as F. And you can apply this model to see what predictions it makes on the inputs from the training set that you just trained with. Well, often you expect this to be very close to the ground truth labels, but it's not perfectly identical. So there is a slight difference for many reasons, right? For example, if you're using cross entropy loss, you know that in order to minimize that, uh, sometimes your weights need to actually be infinite, so with the so if you use these predictions and treat those as training labels and retrain another model from scratch, so the input components are the same as before, you just replace the labels with the predictions. You get a second model, which here I show its predictions by F1. And again, use these predictions as new target labels and retrain third model and so on. So it turns out empirically people observed that some of these intermediate models trained this way actually have a better generalization performance on the test data, on the unseen data. But why this happens has been a mystery because there is no external information coming from anywhere. You're just looping over the training. each time resetting and the weights retraining from scratch. But somehow this dynamic is doing something interesting that makes these intermediate models better than the one that was trained on the original set of data. So why this happens again has been quite a mystery, but I think today we can provide some understanding what's happening there. So when we started studying this problem, we started from something simpler. Instead of deep learning, we started from simple regression setting. But interestingly, this phenomenon is still present in even in simple regression settings. So by applying self-distillation, you can get models that have a better test performance. But working in this regression setting enables us to do some analysis, which otherwise in deep learning is intractable. So this is the regression setting that I'm considering in this talk. We have a bunch of training points, which I show as xk, yk. X is a vector, y is a scalar. And we are using L2 loss. So we are subtracting the prediction from the ground truth label, square that, add it up over all training examples, and that's the total loss. And then you want it to be less than some error tolerance, epsilon, right? Okay. So there are many functions, actually infinitely many functions in the space of functions, right, that can pass through these points or pass close by these points while satisfying this epsilon requirement, right? So which of those solutions you eventually want to get out of this framework? Because there are many solutions up to this point, you need to introduce a regularization. The purpose of regularization is to provide some biases that says, okay, I prefer these solutions versus the other. So if I have a bunch of problems that all satisfy my error constraint, which of them I prefer more? So that regularization here is shown by this R. It's a functional. Functional means that it takes a function and returns a number, okay? And it somehow says how relevant this function f is. Usually it's some complexity measure of the function f, so that often we prefer simpler functions that explain the data rather than more complex ones. So that's how we define our f star. But in this talk, we are specifically working with a specific form of regularization, functional. So we write that as a double integral where the function f appears twice, but there is this function in between, the u function, which we call it a kernel function. And this double integral at the end, it eliminates both variables x and x dot and evaluates to a number. So that's how, like for each function, it can return a scalar, which shows how complex, or not. I want to be more general, so maybe complex is not the thing. But in general, like what are these biases that how much you want to penalize this f? Okay, so I want to provide a little bit more insight about what is happening with this formulation. So first, make it a little bit simpler rather than a constraint optimization. Using Lagrange multiplier, we can simply convert that to an unconstrained optimization. So here C is the Lagrange multiplier. Okay. Now, this form of problem has been studied in machine learning even since 80s and 90s. So you can see one example reference here from Tommy Poggio and Girossi with more than 4,000 citations. So this is well-studied problem, okay? And in a second, I'll show you even what is the form of the solution. It has a closed form solution. But first, I want to provide some intuition about what this regularization is doing, this form of like quadratic double integral thing that you saw, what it's doing. So in order to get that intuition, I want to define based on this kernel function. This kernel function basically is associated with some, you can associate this kernel function with an integral operator so that the whole thing becomes a linear operator. Linear operator means that you apply that to a function and get another function. So if you put an integral in front of you and maybe integrate and multiply that with your function, integrate maybe, for example, with respect to dx dag, then you get a function fx as a result of that because x dag is integrated out. So integration with this kernel function, takes a function and returns a function, right? So integral of this u is is called an operator. You can think of operator, if you're not familiar with those, you can think of them as like infinite dimensional matrices. It's not very accurate analogy, but I think it's good for getting some intuition. So in the same way that for square matrices, we can think of eigen decomposition of a matrix, which gives us eigenvalues and eigenvectors. You can think of like eigenbases. Here, eigenvectors are eigenfunctions for a linear operator, and you get eigenfunctions and eigenvalues for that linear operator. So let's denote the eigenfunctions of this linear operator associated with this kernel U by these phi i's, right? This defines a complete orthonormal basis, so we can express anything in that span, in particular the functions f, assuming that they're in the span of this space. So you basically take a weighted sum of these basis functions, combine them, add them up, and you get the function. So that's how you construct the function, okay? And if we plug in this form of f into our objective function, so do you see my mouse pointer here? So here we are moving from the variational form, which was optimizing over a function, to something that optimizes over these numbers a1 to all the way. So it's infinite number, but basically I'm replacing this f with this summation, right? And also the regularizer, this quadratic form, simplifies greatly. So I get this sum of lambda I ai squared. So now instead of like optimizing a function in space of function, I get something that is more intuitive. I'm just looking for numbers a1, a2, and so on to minimize this objective function, right? And now let's see how this regularization is controlling the bias. So this is saying if okay, so AI is the contribution of each of the eigen functions, right? When you want to use it, you get a penalty lambda I, which weights that contribution, and then you add them up. So without that lambda I, this would be just L2 norm of this A vector, which is like all the coefficients, the sum of their square, right? But now these eigenvalues are weighting these contributions before you're adding them up. So essentially, it's penalizing using some contribution of eigenbases more than others. Okay. So let's again have some simple example to get some more intuition about what's going on here. Let's look at the simple linear operator here, just the second derivative of your function. So it's like I'm taking the second derivative of f, square that, and then integrate it from 0 to 1. So this is somehow showing how smooth or rough the function is within this interval of 0 to 1, right? So associated with this regularization, I can identify the eigenfunctions and eigenvalues. How you get these eigenfunctions and eigenvalues out of these operators is not critical for this talk. I just want to provide an intuition. But just think of it as an example, okay? I just want to build the intuition and later use that intuition. So for this specific operator, these are the eigenfunctions that you get, okay? The first eigenfunction is the blue one, and then you go to the orange and so on, yellow and red. And on the right, you see their associated eigenvalues. So it's showing that the blue one is getting the smallest lambda, which means it gets the least penalty. So if you want to contribute this blue curve, it's very cheap. You can use it even with large magnitude. It can contribute to construction of your function. But if you want to use the red one, there's a high cost. So you use that with care, and you're discouraged to use large values of them. And this kind of makes sense because if you look at these eigenfunctions, they are similar to like Fourier bases. So as you increase the higher frequencies, you can get more rough function, and so there's a higher penalty. So that's consistent with our understanding of why penalizing the second derivative, encourages getting a smoother function. Okay, so we will get back to this intuition later. Now, let's go back to our regression setting. So remember, we used Lagrange multiplier, converted this to unconstrained optimization. And I promise you that this problem has a closed form solution. And this is not new, as I said. Here, I'm just showing what is the closed form solution like. Before expressing the closed form solution, I need to give you one more definition, and that's the definition of Green's function, which again is, these are not critical, but I want the talk to be complete and self-contained. So for the kernel U, we can define the Green's function as a function that if you apply this integral, you get the delta function as a result. Essentially, I'm reading the definition. That's the definition. That's the definition of Green functions. And we don't, again, need to worry about how to compute Green's functions from this regularization U. You will say that these are the details that don't matter, but I wanted, at least you know the definition, okay? So you can take the U and then obtain its corresponding G, the Green's function, all right? Once you have the Green's function, then you need to build a matrix and a vector. So first, let me explain the vector, which is shown by the small g, or maybe the big G is easier. So let's first focus on the big G. So it takes all pairs of your training data and then plugs them into this Green's function, because Green's function exactly has 2 arguments, right? And these, whatever value it evaluates to, that is the value of the I, or here J and Kth column of this matrix. So the J and Kth column is basically computed based on this evaluation of Green's function. For the vector form, you only use one of the arguments for the training data. The other argument is just a free variable x. So this generates a vector valued function. So you have a vector, but all the components depend on x. Okay. So once you have these 2, then you can exactly write the form of the solution. So here F star is the optimal solution, and you can see that it's just like a simple matrix multiplication, vector multiplication, and just a matrix inverse. Y is the labels, all the labels when you arrange them in a long vector. Okay, so all the vectors are constituting this vector. All the labels are constituting this vector Y. So that's how, I think there was some question. Somebody was.
Yes, there is a question. So.
Okay.
Hi. So is there a condition under which this spectral decomposition and the Green functions exist, or do they always exist for positive semi-definite operators?
There exists, but it's very mild. Actually, in the paper, we have a footnote. I don't recall the exact condition, but we mentioned what is the condition, but I remember that it's very mild. So you can almost, think that it exists all the time. Okay. All right. So before again moving to the main contribution, let's pause for a second and see what are some interesting connections we can find here. The first thing is that you can observe a connection between this regularization framework and kernel regression, because those who are familiar with kernel regression recognize this yellow box. That's essentially like G is your kernel matrix. Kernel in the sense of like even SVM. So you have a kernel function, and then you evaluate it at all the pairs of training points, and you get the kernel matrix. And then the way the solution is also computed in kernel regression is like exactly the same form. I just name it G, there it's denoted as K. So this is showing that this regularization problem, which initially had this double integral and all that, it eventually is equivalent to a kernel regression. And the kernel is related to that function U, which was basically the core of that regularization penalty. So by seeing this connection, now we see the next connection, then maybe we can relate this to neural networks due to NTK. So NTK is an idealization of neural networks where you have infinite width. And it's shown that in that regime, training the neural network is equivalent to a kernel regression. So this is admittedly a loose connection to tell what's going on with neural networks, because practical neural networks are not infinite width. But at least I hope this provides some noisy approximation to what's happening in neural networks. And also later, I'll show some empirical result that our theory is consistent with what we see with real neural networks. All right. So now with all this setup, let's focus on self-distillation. So I need to introduce some basic notation. I think I already defined the vectorized Y, which was just concatenation of all of my training labels. And I can do the same thing for the predictions. So the predictions I get, I can arrange them into a long vector and get a vector, which I show by vector F, bold F. And it's easy to show that this F, according to the closed form solution I showed in the last slide, has this form that you see on the right. So instead of the small g, once you evaluate all your training points, you just get the whole matrix. All right, so now we know what, okay, so what happens in self-distillation? We can take this solution, this closed form solution, as the 0th round of self-distillation, like what you do with the regular training. So what we do in self-distillation is now take this prediction, F0, and let Y1, which is our new target label, to be this F0, and then solve the obtain the optimal solution again. So F1 here, everything is the same except that Y1 is like new labels, and then I replace the definition of Y1 with what I had above, right? So I get this one. And you can repeat this process for even T iterations of self-distillation. You get this product that you see on the last line. Okay, so this product may look like a power iteration, but it's not quite a power iteration, because this constant Ci, the Lagrange multiplier, can change from one iteration of like training to another iteration of training. Because even though like our training threshold is epsilon, the Lagrange multiplier can be different because it provides the right balance between fit and error, and our fit is also changing. Like in each round, I have new training data, right? New label. So this
can I have a question? Yeah, so I wonder, is this G times Ci identity plus G inverse matrix commutative or not commutative?
Commute with what? So you are saying
commute with itself. Commute with itself.
With itself. You mean just moving G and then the inverse parenthesis?
Yeah. For example, whether A times B equal to
it commutes, and in a second it will become clear why it commutes.
Okay.
Actually, it commutes when I think these. No, actually, it commutes always.
Okay, cool.
Yeah, but in a second you will see why it commutes.
Okay, thank you.
Okay, so yeah, this could be a perfect power iteration if this C was constant, right? But it's not. So this complicates a lot the whole story and the analysis. Unfortunately, there is actually no closed form to resolve this recurrence, which is like this long product, to something simpler. And in the paper, a lot of effort is just going into getting bounds here and there in order to understand how this F is evolving as you increase T. Okay. But for the sake of this talk, which I want to just make the high level point, I think it's okay to assume this C is constant. It greatly simplifies the analysis and understanding the result, while I think it maintains the underlying phenomenon very well. So we don't lose much fidelity in terms of what's happening with self-distillation. So for the sake of the talk, I assume CT is constant equal to C. If you want to see the advanced one, it's in the paper. All right, so if I make this C constant, then my problem greatly simplifies, because now I can basically convert this long product into just a power. So you can see that I'm raising the thing inside the parenthesis to power T plus 1. And now the problem has much nicer form. On top of that, what I'm doing is also doing eigen decomposition on G. So show the eigen vectors of G by vectors V, and the eigenvalues by the diagonal matrix D. Now, because here, okay, now we get to Tron question. Here, because everything here is either identity matrix or inversion or G, none of these changes the eigenvectors. right? So the eigenvectors are fixed. And I can actually push out the eigenvectors. So V and V transpose go to the both ends, and everything in between is diagonal. And so because of that, they can commute as well. Okay, but this is so this is when C is constant, but I thought about it, and even when C is not constant, I think you can still do the same thing, because the key is that you're adding a multiple of identity and matrix inversion and multiplication, none of which changes the eigenvectors. Okay. All right. Now, let me relate this to the earlier intuition that we had about the regularization operator and eigenfunction and eigenvalues of that. We moved a long way from there to here. So some of that connection may have been lost. So how is this related to those? So the eigenvectors of this matrix G, you can think of them as eigenfunctions of the underlying operator that we use in optimizing this. Except that, okay, this is a finite dimensional thing, so it's like a subsampled version of that continuous function. So actually, if you take these eigenvectors, plot them as like dots, you will see that this dot plot is kind of very nicely like going through the perfect eigenfunction. So this is just you know, a discrete version of that eigenfunction. It preserves the trend, so high frequency, low frequency, they're all there, just discrete. And the eigenvalues are related in an inverse way. So if I was having a large eigenvalue there, here my eigenvalue, like the entries of this matrix T, are 1 over that. So basically here D is the contribution. There D was, or their eigenvalue was the penalty, right? Now here, because it's 1 over that, it's kind of saying how much it encourages contribution of this eigenvector, right? Which you can see here, right? So if okay, maybe, yeah, maybe I just take it as granted, because I don't want to spend too much time at that. I have other slides to get to, but that is the connection. Okay, so if, like, again, if some eigenfunction there was getting a lot of penalty, it means that the equivalent eigenvector here is having a small value. Okay, so it's encouraging that contribution. All right, so now let's see what happens at the limit, because that's the easiest to think about. So because this is raising everything to a power of t, remember this D matrix is diagonal, right? So you can think of these entries on the diagonal independently. So you have one of the eigenvalues, like lambda, and then what's happening is that you're dividing lambda by C plus lambda, right? So simple ratio, lambda divided by C plus lambda. And then raise that thing to the power of t, or t plus 1, right? So what's happening here? So this is saying that as t becomes larger and larger, you are exaggerating the difference between large and small value eigenvalues. If somebody was like large, and remember, these are all less than 1. I mean, you can see that because lambda plus C plus lambda, and C is non-negative, so it's always less than 1. So if somebody is close to 1, like 0.999, by raising that to power of t a couple of times, it still, you know, remains a large number. But if you have something small, like 0.001, apply, like, raise it to power, same number of power, it shrinks very fast, right? So it means that very quickly, the eigenvalues that were small becomes extremely small relative to the ones that are dominant. So at some point, you can even consider their contribution to solution as negligible. They contribute nothing compared to the larger one, okay? And this is basically what's happening in self-distillation. This is the key takeaway. Okay, it basically plays with the eigenvalues of your Gram matrix this way. So again, if you want to relate that to the picture we had about eigenfunctions, okay, small eigenvalues here, remember, are the opposite, are corresponding to the larger eigenvalues there. So it's saying if somebody was getting a penalty, like the high frequency, the red one, now after a couple of rounds of self-distillation, I increase that penalty for that red function enormously compared to what I had for the blue. So I further discourage use of high frequency components for participating in the solution. And so as a result of that, I get even smoother solution, right? Because I'm completely banning use of high frequency component, right? So that's exactly the regularization that's happening if you do self-distillation, as simple as that. It just amplifies the regularization effect, but amplification is a non-linear way. It's not like multiplying your, I don't know. So you cannot get this effect by ridge regression and, you know, multiply like your coefficient of ridge regression. If you just increase that, you don't get this effect. This is a nonlinear way of manipulating your eigenvalues, right? So it's a different type of regularization. You can never get this with ridge regression. And this essentially, in my opinion, is sparsifying your gram matrix, because relative to the larger eigenvalues, the smaller ones become smaller and smaller to the extent that they're negligible. And so you can basically say they don't exist. So they're almost zero. And that's how you're progressively making this matrix of G of lower and lower rank. Okay. Okay. So far, so good. All right. So let's see what implications it has for generalization. First, I give you something more intuitive, and then I can also give you a more formal result. So in order to see intuitively how this is controlling the capacity of the model, let's do a simple renaming. It's not complicated. I'm just naming, I'm defining this Z0, which is essentially the rotated label. Now I'm rotating it by this eigenvector. And PX, which is rotated, again, function G, which is a vector function. So it's just a new naming, but it makes the story more clear. So now we can express F star as I show here. And now let's see what's happening here. You can think of the solution as being constructed by a weighted sum of the labels, right? Because now these are diagonal, right? So it's just saying in this rotated space of labels, okay, I'm like taking some weight from each of these labels, combine them to construct my solution. Now, when this matrix becomes lower and lower rank, it means that you are using actually sparser and sparser. It means that you are using fewer and fewer number of labels to participate in this reconstruction. So it becomes more and more difficult to perfectly fit your training data. It's a capacity control now, right? Except that this Z is not the actual label, it's rotated label in some space, but still the same. Like instead of using the full information on Z, as my diagonals become sparser and sparser, I only use a smaller and smaller fraction of these Z's. And so it becomes, you know, less subject to overfitting. So that's the intuition. Now, okay, so this is a little bit more formal way of saying how that can relate to generalization. So again, here I'm showing the form of the solution on the green box. But the important thing is that you basically what here you can show is that after running self-distillation, let's say after 2 rounds of self-distillation, you have a model, right? Now you can prove that for this model, there is an equivalent standard kernel ridge regression that if you train with the same training data, it gets exactly the same function. You get exactly identical prediction. And the kernel and the eigenvectors of that kernel are the same as eigenvectors of like these 2 rounds of self-distillation, but the eigenvalues are related according to this identity that I'm showing. So here, the DAG is like K shows the like the case element on the diagonal, and DAG means the equivalent like standard kernel ridge regression, and DKs without that DAG are the eigenvalues of your kernel, that's the eigenvalues of this G that we were talking about, which is associated with the regularization, right? And there is this relationship, so you can build an identical problem, identical kernel, that training with the same training that it gets you exactly the same function. And the key is that this function increases in T, which means that the decay, which is the eigenvalue of the equivalent gram matrix, is decreasing in T. Okay, why is this important? Because if you are familiar with the literature of kernel methods and standard generalization bounds, one of the most standard bounds there, very simple bound, is just trace of your gram matrix. So it gives the key quantity. The rest of it is just, this standard confidence delta and, number of samples and all that. But the key part that captures the aspects of the kernel is just a trace of the gram matrix. So because all the eigenvalues here are shrinking, so does the trace, right? So this is showing that for the equivalent problem, now we can use the literature of generalization bounds on kernel regression settings and show that, okay, because trace is small, so you get a good generalization. All right. Okay, so I guess let's see how much time we have. Okay, maybe I can still explain this. Okay, so here I'm basically going to now show you some results. Two kind of results. First is controlled experiments. We have the same toy example that I showed earlier, but now we know everything. We know the exact Eigen function and all that. And we can see what happens if we do self-distillation. Okay. So first of all, I'm visualizing here what is the Green's function of that second order derivative operator, but that's not critical. I just wanted to be complete. I'm showing that. But the toy problem itself is that now we have noisy training samples from an underlying sinusoid function. So the in figure B, the orange curve is the underlying sinusoid, and the blue dots are our noisy observations. So if you just do, standard ridge regression, you get the blue curve. But now in the figure C, I'm showing how the solution is progressing as you apply more rounds of self-distillation. So the blue is similar to what you see in B, but already in the second round of self-distillation, which gives me the orange curve, I get a much smoother curve, and it's much closer to sinusoid. The further iterations don't do much smoothing, they just shrink the magnitude of the function. Okay. And here I'm showing what happens to the eigenvalues of this matrix G. Okay, so here initially, again, these eigenvalues and eigenvectors are completely function of your regularization operator from the second order derivative, right? So they have nothing to do with your training data. Initially, your eigenvalues are distributed like this. So it's quite dense. After one round of self-distillation, you see that the smaller ones shrink very rapidly, right? They shrunk a lot. And by 4 rounds of self-distillation, you can maybe argue that there are only 1 or 2 eigenbases that are really contributing to building your solution. All right, so in the interest of time, I think I skipped some of the details here and maybe get to the deep learning experiments, which might be of interest. All right, so I already mentioned that why this whole kernel regression thing and regularization theory might be related to neural networks through NTK. But now let's see what is even more beautiful about self-distillation. So you don't even need to know what is the underlying regularizer, right? So again, to put this back up a little bit, if we buy the argument that for a neural network, you can get an equivalent kernel regression problem. So if you are okay with that, you don't even need to know what is that underlying kernel. It could be very messy, could be complicated. We don't even need to know about that. As long as it exists, this theory is saying how the eigenvalues of that kernel are evolving over time. And it's saying that, okay, it's sparsifying this contributions of eigenvalues, right? So this is very important because it's very challenging to go and take a deep neural network and exactly, try to specify what is the equivalent kernel. Like even in NTK, this is an active area of research for some of the networks. We know how to build that, but as far as I know, it's not like known for every network. So
can I have a question about the regularization here? So in order to show the eigenvalue decay with respect to the number of self-distillations, it seems that the parameter C, the regularization parameter C, is crucial, because otherwise you may not be able, the eigenvalue divided by itself may equal to 1. So when you multiply these quantities together, there's no decay. So I think that for kernel ridge regression, C is just a regularization parameter. So I wonder, what about for neural network training? If there's no, for example, weight decay regularization, is it still possible to apply your statement to knowledge to self-distillation in neural network training?
So for neural network, you're saying there is no weight decay?
Yeah, if we are not using weight decay, then
yeah, you don't need to use. I see. So let me see. So you have. Yeah, if there is no, if your regularization coefficient is literally 0, then yes, I think you lose the connection. But even if you have a tiny bit of regularization, then this kicks in. So I think this is more like a technical issue than, because the moment you have even a very tiny regularization, then this self-distillation happens. And here's actually why. Here's a better explanation. So if you have 0 regularization, and I say regularization, not just weight decay, 0 regularization, then your predictions are exactly identical to ground truth because you interpolate the data, right?
Right.
Assuming that yes, your family of models has the capacity, which is the case in this study. We are assuming this.
Oh, okay. Right? I see. Then the predicted label is identical to the ground.
Identical, so you don't gain anything by retraining. But the moment that you have even a tiny regularization, this prediction small to be different from the ground truth labels, and that helps.
Yeah, that makes a lot of sense. Thank you. Yeah, I understand now. Yeah, thank you.
Okay, great. Okay. All right. So any other questions so far? I guess after this, I just have some plots for experiment with neural networks. Okay. So here we show some results on ResNet and VGG. I have the VGG results in the paper because they are very similar, so I didn't want to repeat. But these plots are specifically for ResNet. And we have trained them on both CFAR 10 and CFAR 100. Okay. So on the horizontal axis, you see the number of self-distillation. So this is not the iterations of the SGD. Each dot here is a fully trained model to complete convergence. And okay, now let's look at the 2 plots on the left. So I guess these are for CFAR 10. Okay, so one of them is for test accuracy, one of them is for training accuracy. Let's first look at the training accuracy. That's easier to explain. We are saying that each round of self-distillation is, limiting the expressivity of the model. As we saw, it's encouraging using less and less number of, labels, rotated labels. So it cannot perfectly, fit the training data at this point. So we expect as each round of self-distillation, is progressing, it becomes harder and harder to fit the training data, meaning that, okay, the training accuracy should drop. And that's exactly what we see here. You should see this for any regularization, right? So it's showing that, yes, it's doing some regularization. But now the more interesting curve are the test ones, which shows that initially you start gain from this regularization, right? After about let's say 6th round, I think is the peak or something like that. So after 6 rounds, you get the most from self-distillation. But if you continue that, you start to over-regularize it, right? Because this is like a regularization whose strength is controlled by number of rounds that you apply. So initially, it helps you to maybe avoid overfitting. But of course, if you do it forever, at some point it starts to over-regularize. And based on this theory, you expect it to decline, right? You expect the test performance to decline because you're making the model weaker and weaker. And to the best of my knowledge, this phenomenon, like this part of observation was not even known before our experiment. Like people usually do it for 1 or 2 rounds and they see that it kind of goes up and then it kind of stays there. Like this is like where you see almost like a small slope. And then they didn't continue further. So some people were thinking, okay, maybe the performance saturates after that. But here we are showing no, it actually goes down precisely because this is a regularization. And similar trend is with CFAR 100, training going down consistently and tests going up and then going down. All right. So I think I covered things on time. So with my last slide, let me talk about some open problems, especially for this audience. I think there are a lot of graduate students looking for problems. So maybe this is of interest. I categorize it to applied problems and theoretical problems. So for the applied problem, I think the biggest question for me now is whether we can leverage this understanding that we built from this theory in order to build efficient algorithms that can achieve similar regularization effect in one shot. Right now, the only way we knew was to do, more and more self-design. This is very expensive. Each time you retrain from scratch. But now, whether with this, you can actually build a regularizer that explicitly, tries to encourage your kernel, which is induced from this neural network, to be of lower rank. So if this is doable and it's efficient algorithm, I think this is of big interest. And the theoretical ones are, okay, I think the low-hanging fruit is just extending this analysis to cross-entropy. I say low-hanging, but I'm not sure how complicated that may become. It looks like low-hanging. But the more interesting thing, ambitious goal, is to go beyond this RKHS setting. So this is essentially the reproducing kernel hybrid space setting, which corresponds to the exact quadratic form of the regularization that I consider, right? So this is a very specific form of regularization. There are regularizations that don't fit into this form. This form is very nice because everything, will transform into kernels and like kernel regression. And then this also had closed form and we did all that. But if you consider other kinds of regularizers, whether you can still show something. So these are like 2, I think, important theoretical questions. All right, with that, I conclude the talk and thank you all for listening. And if there are more questions, I'm happy to take those.
So I probably want to ask a general question. So do you see any relationship here between this kind of regularization and early stopping?
Yes, I had one slide. So I skipped that because I was worried that I may not finish on time. But now that you asked this, let's get to it. Okay, so this is exactly. So this is not strict at 5, or is it? Should I stop strict?
Oh, no, that's fine.
No? Okay, so let me then cover this slide. Okay, so early stopping. First of all, what does it mean? There could be many definitions. Here's one general definition: any procedure that cuts convergence short of the optimal solution. This actually is an advice from Behnam Neyshabur. So he said this is a general enough definition. And now there are different ways that we can realize this. One of them is if you're using SGD, for example, reduce the number of iterations, right? So stop early in the training process. But this is not applicable to our setting because here everything has closed form, right? So we don't run SGD. You can, but the analysis doesn't depend on, like I didn't consider the SGD. So we use the closed form. And so it doesn't apply to our setting. But there is another way to basically cut the convergence short of optimal solution, and that's by increasing the loss tolerance, right? Because again, think about even thinking about this SGD, cutting the number of like iterations short, that makes the training to stop at a larger value, right? If instead of like training until full conversion, I stop early, then I end up with a larger training error at that point, right? So you can just take that as your criterion for early stopping. Just say, I reduce my error tolerance. Whenever my error reaches this epsilon, I stop, right? So you can increase the epsilon, and that's some form of early stopping, but that is applicable to our analysis. There is exactly epsilon in all of our formulas, right? So, all right, so what I'm doing here first, I'm showing, again, reminding you what is the form of the solution, right? So like a standard training, just one round. So you get what I show here with Z0 and C0 and PX, right? So this is what you get with just one round of training to full conversion. Okay. Now we need to discuss how this C relates to choice of the epsilon, right? So, okay, first let's see what is the scenario when C is very large, right? So remember, C was the coefficient of the regularization, right? So if you choose a very small C, that means that you are taking a lower epsilon, right? Sorry, you increase the epsilon, right? Because you are basically penalizing the no, actually, wait. It's the opposite. Yes, larger C, because you penalize the regularization more. So I keep confusing this, but okay. Regardless of that, so either C is small or large, right? When you make epsilon large or small, either C is small, right? That doesn't matter. The whole point is that you are varying epsilon. That's a way of introducing early stopping, which it translates into moving the C0, right? Okay, so when C0 is very large, let's see what happens. In that case, the thing dominates by the identity matrix, right? So I can basically say that it's approximately the D itself, right? Which is, essentially the eigenvalues are the same as what they used to be. There is no sparsity pattern, right? But when C is very small, then okay, then this thing is almost zero, right? I don't know if you see my mouse pointer, but this thing is almost zero, and so this this predictor becomes like identity, and this is the densest possible diagonal matrix up to scale factor, right? So okay. Oh, okay. So this is what you get with early stopping, right? So at best, you end up getting this solution, because this is the opposite. This is the most dense problem, right? So even if your eigenvalues initially had some maybe small values or zeros, right? This is the best you can hope for by just tuning this epsilon, because the other way just makes things worse in terms of sparsity, right? Sorry, is it clear where I'm going with this? So you just do one round of training, because we are not doing self-distillation. We are just doing early stopping, right? So that only changes the value of C, right? And I'm saying regardless of value of C, if you do one round of training, you are between two regimes. Either this matrix boils down to identity matrix, which is a very dense matrix, or at best, in terms of sparsity, you maintain your original sparsity. While in self-distillation, we showed that like in each round, you are able to improve a sparsity, right? So no value of C is going to improve a sparsity than what you originally had in D here. So this is showing with early stopping, you cannot get the effect that you get with self-distillation.
I see.
This is not saying that early stopping is not useful. I'm just saying these are different type of regularizers.
Yep. So one other question. So in self-distillation, you are trying to kind of, instead of fitting the actual labels, you are trying to fit the predictions, right, of the original model. So it's kind of considering all those uncertainty probably that we have, or making the problem a little bit, using either more information or making things a little bit more uncertain. So is there like a probably philosophical relation to data augmentation, where we try to kind of either generate more data or kind of mix up the labels to kind of making the problem more uncertain? And
Maybe there
it
is.
may not be mathematically very
No, I think we
related.
want to see, yeah, what is intuitively doing, right?
Yeah.
And I had a different explanation. So maybe somebody can also relate it to augmentation or mix up and things like that. But my own like intuition is the following. So this is basically removing the noise in labels, in my opinion. Why?
Yep.
Because let's say you wanted to remember that sinusoid curve, and then we had noisy observation, right? So a lot of points were nice, but let's say you have some points that are outlier, right? So what happens with self-distillation is that when it reduces uh, the capacity of the model, right? So the label, okay, so maybe I put it this way. So the labels of the points that are already nice fit are less affected by that, the prediction, because the model has some biases. Like if it's a neural network, right, it has some biases. As I said, it doesn't produce identical ground truth labels, right? It may be close, but not identical. So if you have some nice images, because it's consistent with the biases, like convolution makes sense and the pooling makes sense for all of those nice images, then okay, those are predicted as they are. But because self-distillation is like making the model capacity lower, it becomes more difficult for it to fit these kind of outliers, right? So its prediction is going to be projection of that label to something that within the vicinity of this smooth sinusoid, because the space of models is now limited. So instead of like being able to fit a sinusoid and suddenly a spike, self-distillation has reduced the capacity of the model, so it cannot fit that point, that spiky point. But it makes predictions, right? So whatever predicts for that point is now its projection to somewhere close this sinusoid, right?
Yes.
So the next time around that you train it, it's no longer an outlier, it's actually contributing, right? Because now it's consistent with the biases, it's consistent with the underlying meaningful biases that were in the neural network. And why you could have noisy labels, sometimes it's not even a human error in annotation. Sometimes it's because we build these discrete labels on images, it's like an artificial way to like map an image into these specific labels. For example, consider an image of a man that is riding a bike. Suppose this image is in image, right? The label, either the ground truth label, either is a bike or a human, right? So it penalizes the neural network incorrectly if, for example, if let's say the ground truth is a man, right? So the ideal prediction would be half man, half bike, right? But because the label is just man, then it's like going against what is natural prediction for this. So it's kind of like noise in the construction of the labels at that level, not error in human annotation, but just because we are introducing this artificial imposing this artificial way of discrete labels on an image, which is naturally not like one class, right? So this could happen, and then if you force the model to predict this image as a human, then you are overfitting, because the right thing is not. Next time it can see a bike, alone, if it knew that this image was half bike, half human, it could leverage that to make the prediction of bike. But because you penalized, you said, oh no, this is not a bike, it's just a human, So it was just a wrong, bias. So by doing self-distillation, those kind of images are basically their prediction is projected into something that the model can still represent within the realm of sensible predictions of images. And now if you retrain with that, it's really like a useful point. It contributes and corrects your training, and you get a better curve. So that's my intuition. And this kind of noise, as I say, it's not human annotation. This can happen like in ImageNet or other places. So it kind of cleans up that noise based on the biases, internal biases of the model, right? And we know these biases are good. Like the whole reason that why neural networks is now, I think, state of the art in image classification is because it has the right biases. It has convolution, which has been, known to be useful for image processing forever, right? Or it has pooling, which gives some invariance. It has this hierarchical representation of image, which is consistent with multi-scale and multi-resolution representation of image. So it has all these good biases, so it can pick up, I think, the right thing, but then we force these artificial wrong labels that we don't want to, like, you don't want it to overfit to those, because then it can fail, like this bike and human. Later, if it sees a bike, if it's overfitted to that image to predict it as human, then it fails to predict the bike.
Okay, thank you so much, Hussein.
You're welcome.
So thanks a lot for the talk. If there is no other questions, probably we can finish the seminar now. And thanks again for your time. It was really interesting. I enjoyed a lot.
Thank you very much again for
Thank you.
Inviting, and to everyone who attended this talk.